Okay, so in this section of the course, which I think you'll find the most interesting, we are going to go over actuators. So the section has two parts. The first is general actuators, for example, linear actuators, rotary actuators, and so on. And the second part is about motors, because one of the most common form and most useful form of actuator are electric motors. Now, I realize there is other actuators too, like hydraulic motors, pneumatic motors, and other things, but since the course only allows us basically 1 month, or a bit more than a month, to deal with actuators and motors, we'll limit it to electromechanical actuators. We'll just talk a little bit about electrostatic actuators, because electrostatic actuators, as you know, can only generate very small forces, but for some reason electrostatic actuators are very important in recent years. So while for dozens of years or tens of years nobody built any electrostatic actuators. So can somebody guess why suddenly are we using a lot of electrostatic actuators, and can you give me an example of an electrostatic actuator? The assignment. Yeah. So, yes?
The electrostatic will scale better when you get into a small...
and where is it? That's what... Excellent answer. Okay, because there is a lot of activity in MEMS, and it turns out, for the same reason when we talked about sensors, I explained that when you build large sensors, a lot of them have coils, but when you build miniature sensors, almost all of them are electrostatic, like capacitance gauge and so on. The same thing is true for actuators. When you build large actuators, almost all of them are electromagnetic, because you can make big magnets, big coils. Now in MEMS, A, it's difficult to make coils. B, the forces which you can get with electrostatics are comparable to what you can get with electromagnetics if the scale is very small. And the reason is, roughly speaking, that you can get very strong electrostatic forces when you have very small gaps. Because we talk about later on next month, we'll do the derivation, how the force relates to the gap. But when you have very small gaps, you have very small electric fields, you can get comparably strong forces electrostatically. Now magnetically in MEMS, you have very little room there for coils, very little room for magnetic material. So the forces are no better than electrostatic forces, and it's difficult to make coils in an integrated circuit process. It's easy to make capacitors. That's the easiest. All what you do when you make a MEM, you just have a sacrificial layer, you etch it out, and you have a gap. And if you put a voltage across the gap, you get a force, and you can have a cantilever which bends and so on. So because of that, when you scale things down to very, very small, electrostatics are very useful, and because of MEMS, there is a lot of electrostatic actuators being used, so we'll devote one lecture to cover the theory of electrostatic actuators. So the next question is, can you give me an example of a MEMS which has an electrostatic actuator? Not sensors. We talked about MEMS accelerometer, they all have MEMS pressure gauges, they have electrostatic sensors, capacitive sensors. But can you think of an electrostatic actuator in MEMS? Say one we have in this room. Yes?
Piezoelectric.
Pardon?
Piezoelectric.
Piezoelectric is not... that's a good answer, because piezoelectric is some kind of electrostatic actuator. I'm not sure we have it in this room, but I can't think of any device in this room which will have a piezoelectric actuator, but that's a good answer. Because piezoelectrics are certainly in this building, we have piezoelectric. But what about an purely electrostatic actuator that we have in this room? The assignment, please. Yeah. So, what can somebody think of electrostatic actuator? I'll give you a hint. Not only do we have one, the assignment. And not only do we have one in this room, we have 1 million electrostatic actuators in this room. Yes?
EMD beaters.
Pardon?
EMD beaters.
Sorry, I couldn't hear you. The what?
TMD meters they use for projectors. Micrometers.
Mirrors, very good, very good. In this projector, there is most likely, most big projectors have a device called a digital mirror device, or DMD. And what it is, it's a grid of 1,000 by 1,000 electrostatic actuators which are used as light modulators. So the way these things work, you have 1 million mirrors which can tilt electrostatically, and the mirror either directs the light to the screen or directs the light away from the screen, and therefore that's how we get the image. So this is the most popular application today of electrostatic actuators. And that was developed by Texas Instruments, and they call it DLP. When you see some projectors, they have this logo on them, and it says DLP, which stands for Digital Light Processing. So when you see this logo, it means this projector has 1 million electrostatic actuators. Yeah. So anyway, so it turns out there are more electrostatic actuators in this building than any other kind of actuator, because every room in this building has 1 million electrostatic actuators, which is quite surprising. Okay, so certainly not this number of any electromagnetic actuators. Okay, so because of this DLP, which was originally called DMD, that has a long history, this project. It started many, many years ago. When we talk about electrostatic actuators, I'll talk more about it. But I just wanted to give you kind of the big picture. The big picture is actuators and then there is 3 families. There is electromagnetic, there is electrostatic, and there is fluidic. And we're talking about actuators useful in servo systems. So fluidic is, for example, hydraulic. Okay? But these we are not going to cover. Obviously, you've seen that we're not going to cover. Now, electromagnetic, there are 3 categories, which we'll cover in a minute. And electrostatic is pretty well all the same. They're cantilevers. They're all based, there is a ground plane, there is a cantilever, and it's being bent, or a block of piezo, which we should also classify as electrostatic. When you put a voltage on it, it shrinks. Okay? You can make it expand, you can make it shrink. So we'll cover this briefly. Piezo. We'll cover briefly piezo and electrostatic. Most of the months of March we'll talk to electromagnetic. Now, electromagnetic come in 3 flavors. One is called moving coil. I'll just redraw this part of the diagram bigger here. So this is electromagnetic actuators, and the 3 flavors are moving coil, and this is moving magnet, and the last one is moving iron. And the name says it all. Moving coil is basically a coil in a magnetic field. If you put a current in it, the coil moves. Moving magnet is a magnet in the field of a coil. If you change the field of the coil, the magnet will move. And moving iron is a piece of iron drawn into in the magnetic field. Okay, so I'll get into much more detail of those. But first, some examples. Can you think of a moving coil actuator? Like each one of you possesses many moving coil actuators. I would say every person today possesses at least a dozen of moving coil actuators. Maybe you don't know that you have them, but you have them. Yes.
Speakers.
Speakers. Excellent example. Probably one of the most common moving coil actuators is a speaker. It has a coil in a magnetic field. And that's how it makes sound waves, by moving the coil. Any other moving coil actuators that you possess?
Stepper motors?
Okay, stepper motors turns out are moving magnets, because the way they work, the coil is stationary and the rotor is a magnet, but you gave a good example for this one. Okay, so this will be like a stepper. Like a regular motor is moving coil, like a DC motor. DC motor, speaker. Any other, so let's stay with moving coil. Any other example of moving coil actuators? Again, something all of you have. I'll give you a hint. All of you have now, but you would not have in 10 years. Disk drives. Like, how does a hard drive work? There is something has to move the arm to different places on the disk to find the data, right? That's a moving coil actuator. Okay, so this is a hard drive. And then you can think of many more, okay? If you have autofocus in your camera, there's many places where you have moving coil. Meters, if you have any kind of analog meter, all analog meters are moving coil actuators. Almost all analog meters are moving coil actuators. Okay, moving magnet, stepper motor. Now moving magnet, actually there are many other of those actuators, but you probably never seen one. So I don't think you would be able to think of any other example of a moving magnet actuator, but give it a try. Where besides a stepper motor and say a synchronous motor, which is the same as a stepper motor, so where besides synchronous motors did you see a moving magnet actuator? Yes? Solenoid is actually moving iron, because the thing which moves is not a magnet, it's just a piece of iron. Okay? So, but you gave a good example for that. So solenoid is moving iron is typically a relay, a solenoid, electromagnet. Okay, so these are all moving iron actuators, like buzzer, door buzzer, things like this. They are moving iron actuators. Moving magnets are used in a lot of galvanometers and scanning devices, but I'm not sure you had a chance to play with one. That's the most common use of besides synchronous motors. The next biggest use of moving magnet is inside a scanning device, and we'll talk in next week why. Why is each one popular why does each application use a specific actuator? I guess you had a question? No. Okay. So that's an overview of actuators. So let's start with the most basic one, moving coil. So let's talk a little bit about the history of this. Many years ago, people knew about magnetism. People had compasses for hundreds of years, like the Chinese had compasses for hundreds of years. People knew about electricity, first about static electricity for hundreds of years, but then somebody invented the first battery, and then people had electricity, not just static electricity, but continuous electricity. Okay? So who invented the first battery? Alessandro Volta. The volt is named after the guy who invented the first battery. So now people started experimenting. They had electricity. Because if you take dissimilar metals in acid, or even in a base, but at the time it was done in acid, you put dissimilar metals, you get a voltage, you get a battery. Now you can make all kinds of things with a battery. But it's interesting that people didn't realize there is any connection between electricity and magnetism. So what they did with the electricity is they could run it through wires, and the wires got hot. So they realized there is a connection between electricity and heat. They put the wires into water, and they saw little bubbles, which were oxygen and hydrogen, because it dissociated the water. So people realized there is a connection between chemistry and electricity. Okay? So people knew by, say, 1800, by year 1800, people knew that electricity somehow is related to heat, related to chemistry, related to action inside the body, because Volta made the battery following a discovery of Galvani, who saw frog muscles of a dead frog twitch when they were touched by metal, because the metal formed the battery and the dead frog twitched the muscles. And that was what started Volta on investigating it and inventing the battery. So people actually knew that the muscles in the body and the body has something to do with electricity. But nobody knew there was a connection between magnetism and electricity until a Danish professor who discovered the connection of electricity and magnetism. And who his name was? So, Ørsted, excellent. Christian Ørsted. Okay, so the person who discovered there is a connection between electricity and magnetism was Ørsted. I'm not sure I'm right. I'm spelling his name right because I think it's spelled O like the Danish way. But anyway, so he. Okay. So he and how and if you knew Ørsted, so what did he discover? How did he discover the connection between electricity and magnetism?
He accidentally had like a magnet near.
Say it again.
He accidentally had like a magnet near something and noticed that it triggered.
No. Okay, Ørsted actually suspected there is a connection between magnetism and electricity, but couldn't find it. But he was setting up an experiment with wires and batteries, and he had a compass on the table. And when he connected the wire, he noticed the compass needle moved. But he actually knew there should be a connection. Nobody else would have noticed, because the compass needle moved very little. Because in those days the batteries were weak, the currents were small, so nobody else would have noticed the compass moved a bit, but he actually was thinking about it all the time. So and once he saw the compass needle moved a little bit, okay, he realized, he discovered what he was looking for all his life. So when he discovered this little twitch in the compass, okay, which he was looking for many, many years, he did a very surprising thing. He put it aside for 3 months and didn't do anything about it, and nobody knows why. But that's really puzzling. But later on he came back to it and published it and did work on it, and that was the first time there was a connection between electricity and magnetism. And who discovered the opposite, the connection between magnetism and electricity, like what you were talking about? Who discovered that when you bring a magnet near a coil, actually electricity will flow in the coil? Who discovered that? Okay, so this is Ørsted 1820. Okay, that was a compass. So he discovered if there's a conductor, if you put a compass here, the needle of the compass will move. Okay, so and who discovered the opposite, that if you bring a magnet near a coil, it will make electricity? Who?
Henry.
No, Henry built the first good electromagnet. Which pardon? No, but okay, Faraday. So Michael Faraday and this was much later. This was around 1840, something like this. Again, this is around, I think, 1821 or something, around 1840. So it's a rule in electromagnetics. If somebody asks you who discovered, you always say Faraday, because then you're 50% right. Because Faraday discovered, seriously, half of what's known in electromagnetism. So it's always a safe bet to say Faraday. Okay? Because Faraday discovered the transformer, magnetic induction, electric fields, magnetic fields, and basically a lot what we know today. He built the first electric motor in the world. So a lot of stuff in electromagnetics comes from Faraday. Okay, so Ørsted discovered that a current makes a magnetic field. Faraday discovered a magnetic field can make currents, and therefore you can make a transformer and you can have magnetic induction. So but after that, everything was known and people started building electromagnets. People built electromagnets before, but people improved them, like Henry, that built good electromagnets. And by the way, Henry is the one who gave Morse. Morse is the guy who did the Morse code, right, the telegraph. Henry is the one who gave him the tip that you have to insulate the wires. Because Morse was a painter. He didn't know when you make a coil, you have to insulate the wires. Okay? So, by the way, assignment, if you haven't handed it in. Yeah. Okay, so that's a short history. So now let's go back and talk a little bit about the formulas. When you have a magnetic field, and you have a conductor in the magnetic field, when you put a current in the conductor makes its own magnetic field, which we actually mentioned many times and even calculated. So the magnetic field the conductor makes interacts with the magnetic field the conductor sits in, and this interaction of two magnets creates a force. Okay, so that's the explanation why there is a force on a conductor and magnetic field. So if you have a magnetic field, let's draw in a 3D picture. Let's say you have a magnetic field this way, okay, going up. I mean, the directions are just convention. I mean, by convention we say magnetic field goes from north to south, but these are just conventions. It doesn't really matter which way it really goes. The same thing as electricity. By convention we say goes from plus to minus, but actually electrons go from minus to plus. So don't worry about the convention. What's more important is the setup you need to get an interaction. So now you have a conductor here, and if you draw it in 3D, the conductor goes through the magnetic field, and let's say there's a current flowing through the conductor, current I. The magnetic field, the current and the magnetic field and the force which will be created will be perpendicular to each other. So I'm not quite sure if I drew it right. Let's just draw for a moment, not a 3D, but let's just draw for a moment a cross section. This is the current coming out, okay? So now a force will be created, and there is a rule called the right-hand rule which tells us force, but you're not required to remember the directions, just to remember there will be a perpendicular force which is perpendicular to the current and to the field. So the three, the current, the field, and the force are three perpendicular vectors, which also means that if this conductor, say, is not perpendicular to the field, you'll only get the projection, which is perpendicular, creating force. In other words, there are three vectors, right? You have to do the vector product. So basically, the projection, what matters, and you get a force. And if this field is B, the force is equal to, what's the force? If there is a current I, there is a field B, so what's the force? Come on, you did it 100 times in Physics 101. Very good, BLI. The force is BLI, and this you are required to remember. Now, L, if there is one L, this is L. If there is one L, the force is small, because L is short, but you can wind the wire many times. So if you wind the wire many times, you are putting many units of L in parallel, right? So you can explain it two ways. Either you can explain it, you're making the effective L longer by putting many units in parallel, or the easier way to understand it intuitively, you're making the current bigger. Because if you wind the coil with many turns, you end up with many currents, and they all appear like one big current equal to Ni. So if you have n turns of the loop, the effective current is Ni, and that's the way you look at it when you think of actuators. You don't think of the current, you always think of Ni. Because Ni makes it like one big current, N times I, so all the formulas are linear or related to Ni, not to I. Okay, so now what is the problem with this thing? So let's draw here. Now I'm making a top-down view. So top-down view, now the magnetic field is going into the board. Let's say the magnetic field is going into the board. And this is B. B is going into the board. Now let's say I put a conductor like this. Okay, and this unit is L. Okay? So first of all, before I do that, so what would happen if the whole board was covered with magnetic field and I put in a complete loop like this, and what would happen if the rest of the board was also covered by a magnetic field and I put in a current I or Ni into this loop, and the whole board was covered by a magnetic field going into the board? Which direction will the loop move? Where? Let's say the whole board is B going into the board, and I put in a current I. Which direction will the loop move? Okay. Okay. How many people think the loop will move down? Okay. Okay. Anyway, so obviously you weren't listening carefully, because if the whole thing would be covered in magnetic field and I put in a current I, the loop will never move. The reason it will never move, because there is a current I, let's say, going this way, and there is an opposite current I going this way. There is a current going this way, and there is an opposite current going this way. So obviously, if the forces on these two will be equal and opposite directions, the forces on these two arms will be equal in opposite directions. So obviously, if the whole loop is in a magnetic field, it will never move. Okay? In this position. If the whole loop was in a magnetic field in the other direction, you'll get a torque. Okay? So let me just draw that. Imagine now, so this is a loop which is perpendicular to the magnetic field, where the whole loop is in the magnetic field. Obviously it can't move. All the forces cancel out. Now if you do something different, if you put in the loop in the vertical plane, so now we are going to draw it looking from the side. So now if this is now B, and we put in the loop parallel to the magnetic field, so what we see something like this. The current is going in here, and the current is coming out here. So now what will happen is this, that this side will have a force, let's say one way, this side will have a force another way, because the current is opposite. The loop will develop a torque. Now all this you should have learned many, many years ago. Now the other two walls on the loop are parallel to the field. Remember, the loop is like this. It's going outside the blackboard. Now the magnetic field is like this. So this side of the loop and this side of the loop, they don't create any force because they are parallel to the field. And since it's a vector product, so B times I times cosine 90 gives you 0 force. So these two will just derive a torque. So again, if the loop is oriented parallel to the field like before, this is like this, nothing will happen. Okay? Now if the loop is oriented this way, it will try to turn until it aligns itself this way, but in both cases there will be no sideways force. So how do you make sideways force? You have to stop the field somewhere here, so this part is not in the field. So what you have to do, you have to constrain the field. So if you constrain the magnetic field to the dotted line, these two forces cancel out, or they're outside the field. Now here you generate a force, and here there is no force because there's no field. Okay, so now there is a net force, because here there is BLI, here there is nothing, so there is a net force BLI. Is that clear? So to summarize, if the whole loop is immersed in the field, there's either nothing is happening when the loop is square to the field, or there is a torque if the loop is parallel to the field. If the loop is partially immersed in the field, those members which are in the field will create a force, and depending on the structure of the loop and the direction of the current, it will determine the direction of the force. And this shows you already the first problem with moving coil actuators, because if I look at a loop like this part has to be outside the field, otherwise the force will cancel out. So this part adds weight to the actuator but doesn't do any work. But I have to have it because I have to close the current path to a loop. Okay? Now these two parts add weight but create opposing forces which cancel out. Okay, so basically the only part of this whole loop which creates a force is this part. So what you can see here is that this is a very inefficient design. You have a loop, let's say it's a square loop. So you have 4 times weight, but only one of the weights creates force, the other 3 just hang, add inertia and not force. Okay? So you see the first problem in designing moving coil actuators, that if you want to design an actuator for motion, for motion, and you make a simple loop like this, the weight is 4 times each arm, but the force only comes from one arm. Okay? So if you think of kind of the efficiency of the actuator, which is the force over the weight, okay? The MEM is a mass, okay? So this has 4 masses, but only 1 force. Now, if you want to make a coil which generates a torque, situation is a little bit better, because in this coil, which is wound this way, 2 of the arms generate torque and the other 2 do nothing, but at least 2 of the 4. Okay? So here it's only 1 of 4. 1 out of 4 generates force. If you make a loop like this which generates a torque, you have 2 over 4 generate a torque, which is better. Okay? But what about if you want linear motion, not torque? So how can you improve this design to get to a better ratio of dead weight to work producing wire? Because obviously that seems like a very, very bad design if only a fourth of the wire does the work and the other 3 just weigh down, slow down the response. So starting from this, how would you redesign it to have an actuator where this ratio ideally would be 1 to 1, where all the wire produces force? So I'll give you a second to think about it. Okay, so any ideas? Yes.
Instead of connecting in the middle, you could have it go out the bottom so that
Okay, so let's see if I understand you. Instead of connecting in the middle, have it go where? Sideways?
the opposite way.
The opposite direction.
Yeah.
Well, okay, it doesn't help much because you have to close a circuit. Let's say you have a battery here. Somehow you have to close the circuit. It doesn't matter where you close it, okay? So it's true that you can say, why don't I close the circuit right to here? Because in theory I can have just one wire, but if this wire has to carry a certain current, these connecting wires also have to carry the same current. So they'll have the same weight. See, the problem is, the reason it has weight, it has to be made a certain thickness to carry the current. So if you take the battery and connect to here, these connecting wires have to be the same thickness. So in a way it didn't help much, right? See, I drew it like this with a battery inside here, but anything you do still will be a loop of the same weight, and it has to move. So, yes?
Are you allowed to change the magnetic field?
Pardon?
Can you change the magnetic field, or is it a static field?
Okay, you can change it, but then it's a different actuator. It's not a moving coil actuator. So you can do things, you can do it a different way. You can have the coil not moving and the magnet moving. For
Like change the polarity of the magnetic field.
This will not improve the efficiency. If I flip the magnetic field, the force will reverse. In one polarity of magnetic field, the force will go up. If I switch the magnetic field, the force will go down.
I mean, like half.
That is a very good idea. So the first good idea here is saying like this. Somewhere in the middle here, I can flip the magnetic field. And that's an excellent idea. Okay, so I'll redraw the coil. I misunderstood you first when you said switch the magnetic field. And what I'll do is on the first part, I'll use the same magnetic field as before. And on the bottom part, because the current switches, I'll also switch the magnetic field. Now it's very easy to do that, because these are permanent magnets, but you can make it from 2 magnet pairs and just flip over the magnet. So it's not difficult to make a magnet like this. Now when I do that, this current, if I draw it the same as before, let's say we'll make a force this way. Now this current is reversed, but also the magnetic field is reversed, so the force will reverse, so both forces will add up. Is that clear to everybody? Okay. So, which device works like this? something all of you have works exactly like this. The magnetic field is switched in the middle, so both sides add force. Disk drive. How many of you took apart a hard drive? How many? One. See, that's very worrying. See, guys, you're taking a course in electromagnetic actuators. Now, the actuator in the hard drive is the most optimized actuator in the world. Okay, there is probably $1 billion of R&D went into optimizing this actuator, because the overall R&D in the hard drive industry is probably 100 billion by today. But I would guess $1 billion just went into optimizing and tooling and improving this actuator. So aren't you curious to see what the smartest people in the field in $1 billion did? So if you're really interested in sensors and actuators, you really should take apart the disk drive and study its actuator. But you don't have to worry, that is the next assignment. So which is not due yet. It's, you'll do it in a month, but I'll give each one of you a disk drive and you'll have to analyze it. Okay, because that's a shame to graduate from a course like this without seeing the inside of a disk drive. So that's what they did in a disk drive, and now you have 2 out of 4. Because you have 4 weights, okay, and 2 of them produce, okay. Now in a disk drive they did one more trick, because in a disk drive you actually want to generate rotation, because the way the disk drive works, it pivots, it doesn't go in and out. I don't know if you know that the early disks, the big disks like IBM 3380 and so on, they actually went in and out, okay, like this. But the new disks all are rotary. Okay, so because they are rotary, they still did this trick, but they had the coil rotate around an axis. So what they wanted is they could do the same trick, but now this whole coil was connected to a pivot here. So this is a pivot, so the coil didn't actually slide straight, it moved on an arc. But it's the same principle, it doesn't matter, it moved on an arc. But somebody smart figured out that if the coil moves on an arc, because of that, you can improve that ratio. So basically, this was the dumb actuator, how people started. Then people say, just a second, we can reverse the magnets, double its improvement, to get from 104 to 204. But then, when they started making this drive, somebody said, because we actually need the whole coil to turn, not to move straight, we can improve that again. So what is the next step? Yes?
Did they make it not square so that it would be unbalanced?
Beautiful. And what shape should they make it?
Triangular.
Exactly. So the next step is, if we are going to rotate it anyway, why don't we do that? Why don't you make a triangular coil? Okay, so these are the wires. Okay, and then this whole thing is turning, we said, about the pivot. And then we do the magnetic field here. In this part, we'll do it like this. In the bottom part, we'll do it like this. Right? This is a standard aero convention, right? This means coming out, this means going in, right? You're all familiar with that? Yeah. So now this will give you a force this way, this will give you a force this way, because both the current and the field reversed. Right? If this is the current, at the bottom the current reversed but the field reversed. So now we reached 2 out of 3. 2 of the arms produce torque or force, and the total weight is 3. So we reached a ratio of 2 out of 3. So we went from 1/4 to 2/4, but because it's rotary, we could get to 2 out of 3, which is a bit better than 2 out of 4. Okay? But what if we wanted 4 out of 4? What if we wanted to go back to a linear actuator, and we actually wanted every piece of copper to produce force? How do we do that? So something you all own, of course. Very simple. What we do is we do what a loudspeaker does. We lay out the poles of the magnet in such a way that the magnetic field is not parallel but radial. So let's say let's say we have magnetic field which is radial. This is north pole and this is south pole. And it's very easy to make a radial magnet in cross section. Imagine if I have a piece of steel like this and I have a ring of steel which is like this. Okay, all what I have to do is I have to put a magnet here, or two magnets, which this is north, this is south, this is north, this is south. So now the field is going to close like this. So the field, looking from the top, will look like this. The field is trying to go from north to south. Again, all this is conventions, as I said. Okay, so does everybody understand how I made the radial field? Okay, now if I put a loop of wire in the radial field, every bit of wire will have a force on it pushing in this direction. Okay, because remember the three vectors are perpendicular, so I have B in this direction, I have I in this direction, so BLI will come out like this, or like this, depending on the direction of the current. Okay, so if I make the field radial, every piece of copper creates force, and then I get 4 out of 4. It's not 4 anymore, but basically I get 100%. 100% of the mass creates force. Okay? So when we think of the best acceleration achievable, obviously if we are interested in high performance actuator, this construction will achieve better performance than this construction, and this will achieve better than this, and so on. So why don't they use this in disk drives? Because in disk drives this has the wrong form factor, because that's like you can't make it flat. And in disk drives they want a rotary actuator and not a linear actuator. Now the reason, by the way, why people want rotary not linear, because in any mechanism, if you can make it rotary instead of linear, you are ahead. Because a rotary motion is much easier to build, much easier to seal. Right? You just have a ball bearing and you achieved rotary motion. Linear motion is much more problematic because you have slides and so on. You know, think of the human body. All the joints are rotary. Okay, because it's easier to seal. Okay, no, it's serious. That's in nature. You know, nature tries to do everything rotary. Only if it doesn't work, you make it linear, sliding linearly. So robots, all robots are rotary joints. There are some Cartesian robots, but most robots are rotary joints. So in the disk drives, they wanted it rotary, so this actuator wasn't suitable. A, because this is more like a cube. B, because it's not rotary. But in terms of, if we talk about F over m, like the maximum force to mass, which determines acceleration, this is a 100% efficient actuator. Okay, disk drive is 66% efficient actuator. Reversing the magnet is a 50% efficient actuator, and a plain loop in the field is 25% efficient actuator. Is everybody clear on that story? Good. Okay, so I'm going to pass there's a loudspeaker where a part of the diaphragm was cut away, so you can see the coil moving. So this is a loudspeaker which looks like this, and I'm going to pass it, and I'm going to pass a coil out of a disk drive, so you can see this construction. Okay? If you want to see this construction, you can just look at any meter, because any meter, analog meter, it has this kind of coil to generate a torque. Okay? And as an example, okay, let me pass 2 more examples. So I'll start by passing those 2, and then I'll pass a few more examples. So if you want an example of moving iron actuator, this is just a standard solenoid. So this thing all of you have seen. And if you want another example of moving coil and moving magnet, I'll pass 2 electric motors. One is a standard DC motor which has coils moving in a magnet, and one which is inverted, where the way it's done, there is a stationary coil and there is a moving magnet. That's from a floppy disk drive, which is obsolete, but in the floppy disk drive they use moving magnet because for some reason it was beneficial to do it this way. You know, to make the they wanted the big hub to support the drive, because you can say that's just like a brushless electric motor. But in a brushless electric motor, like a stepper motor, the armature is a magnet. But here they actually, the inner part is a magnet. Here they just made it the outer part. So anyway, when you think of moving magnet, think of a stepper motor, or this is just unique because the outer shell rotates around a stationary coil. Okay, but it's still moving magnet. It's like an inverted stepper motor. Okay, so so pass these along, just see a few other actuators. Okay, good. So now the next thing which is of interest in any actuator is to derive the maximum possible performance. Because when you design something, if the servo requires some performance which is just on the limit of what actuators can do, you know there will be lots of trouble. Okay, so you want to compare the requirement of the servo to the theoretical limit of the actuator. I mentioned before the sensor is usually not a problem, so you never have to worry about the theoretical limit of the sensor, unless you want to measure to a part in million or things like that. But in a normal servo system, you never think what is the limit of the sensor, you always think about what's the limit of the actuator. Okay, good. So now, good. Let's see. So let's go back to actuators which are 100% efficient. In other words, all the copper in the magnetic field produces force, and we want to understand what is the theoretical limit. So we have a piece of copper meaning conductor, doesn't have to be copper, but in actuators there is really only three materials which make sense for coils: copper, silver, and aluminum. You never see an actuator with any material other than these three as conductors. So the reason is, maybe I should talk about it after I derive the formula. So just forget the sentence, we'll see it much clearer in the formula. Okay, so I have a conductor of length L. The conductor has cross-section A. Area A. Okay, so the mass of such a conductor will be the density, which is rho, times A times L. Okay? Of course, in the right units. If it's all MKS units, that is the mass of this piece of conductor which carries a current I. Okay? Now, if this conductor is placed in a magnetic field, B, and it's placed in a way that every piece of conductor contributes to the force. So let's talk about the loudspeaker, because that's the only example I showed you, that every piece of conductor creates force. Okay? So the force is BLI. But then you say, just a second, I can make the force as big as I want by increasing I. Let's say B is fixed by the magnet. Typically, I don't know if I mentioned it before, but if you use permanent magnets, you cannot get any B you want. In a permanent magnet with an air gap, it's very difficult to get more than 1 Tesla. The only exception is MRI machines. In MRI machines, they have some enormous magnets, they are getting up to 3 Tesla. But any actuator you will build, you'll never get more than 1 Tesla. This is about limited to about 1 Tesla. Most of the actuators you'll build, it'll be less than 1 Tesla. For example, in a hard drive, B is about 0.8, 0.9 Tesla. And you can bet on it that they optimized it to this. Okay, so B is fixed. L, you can increase L, but if you can increase L, the mass will also get bigger. And you can already see where I'm heading, because I want to derive the force and the mass and divide the force by the mass to get the maximum theoretical acceleration. So you can see where I'm heading, that if I make L bigger, the force will be bigger, but the mass will be bigger by the same ratio, so I don't gain anything. So I can play with I, okay? But what is the limit to increasing I? Why don't I just run the biggest I can? Okay, so there are two limits. The first limit is obvious. If the area is a certain area, I can only run so much current through it before the wire will overheat. Because the wire has a heat loss, I squared R, and the R is inversely proportional to the area. So to carry a certain current, I need a certain area. So there must be a relationship between the maximum I and the area. And indeed, it's not a theoretical relationship, it's some rules of thumb. Because if the wire is heat resistant, let's say the wire has very good insulation, and I don't care if it heats up, of course I can run a bigger I through it. But a rule of thumb for all electromagnetic devices is that you don't want to run a current density of more than 10 amps per square millimeter. That's a very good rule to remember, because a square millimeter is a bit thicker than a paper clip. Right? If you look at a paper clip, is about the wire a paper clip is made of is about 0.8 square millimeter, because it's 1 millimeter diameter. So square millimeter is also like maybe a gauge 18 power cord, the wire inside. So that's kind of a good rule of thumb when you make coils. You don't want to run more than 10 amps per square millimeter, because this power density corresponds to a certain delta T. And if you run it at this density, the delta T, delta temperature, will be moderate. Moderate meaning the coil will heat up 30 degrees or something like that. Now if you run higher than that, the force will go up linear with I, but the heat will go up like the square. So you pretty soon stop gaining. Say if you double this number, you'll only double the force, have 4 times the heating. So instead of 30 degree delta T, it'll go to 120 degree above ambient, which is already pretty bad. So because of that, that's a good number to remember for copper. That's for copper. Okay, so this is roughly approximate. We have to convert this, of course, to MKS unit. So a square millimeter is 10 to minus 6 square meter. Okay, so this is roughly BL times A times some current density number. Okay, and the current density number is, we just call it gamma. Okay, and gamma is 10 amp to square millimeter, or this will be 10 amp to 10 to minus 6, so this will be 10 to the 7th amps per square meter. Okay? So, but the easier number to remember is this, because this has an intuitive meaning, because a square millimeter is your average wire. Okay, so now when I want to find maximum A max, I simply divide F by M, okay, and F is BLA gamma, divided by M, rho AL, okay, and you can see it's completely simple, that A cancels out, L cancels out, and I'm getting B gamma divided by rho. Okay? So the maximum acceleration achievable is very simple, is it's basically 3 constants which are all derived from material properties. So the limit here to the acceleration is derived straight from material properties. You can only get so much B because of air gaps and because of the best magnetic material we have today. You can only get, this can only be about 1 Tesla. Now, this, because of heating, cannot be much better than that. Steady state. Of course, if you give it a single pulse, momentarily, it can be much bigger. But steady state, you plug in the numbers, you'll get 1 Tesla times rho is 10 to the 7th, gamma, 10 to the 7th ampere square meter. And the density, so now you have a choice, but most coils are made of copper. Copper is about 8.8, roughly 8.8 tons per square meter. Okay? So that's roughly 8.8, so 8 times 10 to the 3, so 8,800 kilogram per meter cube. Okay? So in rough numbers, let's call this 10 to the 4th, because 8,800, let's call it 10,000. So very rough numbers, you get 10 to the 7th divided by 10 to the 4th, and you get around 1,000 meter per second squared, or 100 G. So that's a very good number to remember. Let's check the calculation again. That's 10 to the 7th ampere square meter, that's correct. About 10,000 kilograms per cubic meter, so divided by 10 to the 10,000, yeah. So basically the bottom line of the story, that moving coil actuator performance is strictly limited by property of materials. There's no big theory behind it. And B is limited by the quality of magnets we can get. And if we take the best magnets we can get, like rare earth magnets, because we need an air gap for the coil, we are basically limited to 1 Tesla, unless you do heroic measures, like in MRI machines. Okay, and we take copper, which is a very good conductor and a certain power density, divide by its density, we get this. So what can we do better than that? Okay, so first I keep reminding you, this is for continuous operation. If I need an actuator which just has to move a pulse and then wait, move a pulse and then wait, then what I really care is about the average heating, or to be more accurate, I care about the RMS, not the average, and we'll talk about it later. But momentarily I can exceed this current by far, because if this is because of heating, okay, and I only need to drive it infrequently with a pulse, I can greatly exceed this number. Okay? So for steady state, so this is a steady state limit. Steady state limit. If I don't care about heating, if I just need to drive it very infrequently with a huge pulse, I have another limit. Because it does make sense, there must be some other limit, otherwise I could drive it with thousands and thousands of amps for a microsecond, but there must be another limit. So can somebody think, what could be the next limit if I don't have a heating limit? Yes? Impedance. Pardon? Impedance. Okay, so that's a good point, but impedance you can overcome. The reason impedance is a good point because any coil has inductance. Okay, so when I try to drive it very fast with a high current, the impedance will limit the rise of the current, but I can drive it from a current source. So solution number 1, I can drive it from a current source, then I don't see the impedance. Solution number 2, I can make the coil with very few turns of a very heavy current. So drive it with thousands of amps, but have very few turns, and then I don't have much impedance. So the impedance problem has some solutions. By the way, I cannot make the coil without impedance, because a coil without impedance will also generate no force, because they are theoretically linked. Because if you think about it kind of in a bigger picture, the force is a derivative of energy to distance. And the energy in a coil is 1/2 Li squared. So if I can make a coil with no impedance, it will also make no force, because it will have no L. And then the derivative of the energy to distance will be 0. Is that clear? Because otherwise you'd be tempted to think, maybe I can make a clever coil which one turn goes this way and another turn goes backwards to cancel the impedance. But it's a waste of time, because if you cancel the impedance, you cancel the stored energy, which comes from impedance. And if you cancel stored energy, you cancel the derivative of energy to distance. It will give you no force. Okay? Good. So I can get rid of the impedance by driving it from a current source, or by making a coil which has very few turns driven at very high currents. But there must be some other limit. Yes?
Mechanical properties of what?
At some point, that is a third limit. At some point, mechanically, it wouldn't be able to withstand the forces, yes. But between that is very far away. There is a limit much earlier. We hit another limit much earlier.
The tension limit of the insulation material?
Say it again?
The maximum tension you can go between the 2 layers of insulation?
Again, I can get around that. You're talking insulation limit, but I can get around it by making it with very high current, very low voltage. Let's say I make a coil which only has 1 or 2 turns, and I drive it by thousands of amps. So there's very little tension difference or potential difference. So this I can get around. This is actually not a real limit. But there is a very real limit which prevents us from going, say, 1,000 times this value. You can go maybe 10 times this value, but not 1,000 times this value. And that limit is demagnetization. Because when I drive that current, I started this lecture by saying the way I get a force because of the current is this current creates a magnetic field. The magnetic field this current creates interacts with this magnetic field just like you held 2 magnets together. And the force I get, the way the current interacts with magnetic field, is the force I get is like the force between 2 magnets. The magnet caused by that and the permanent magnet. But if this magnet the wire creates is enormous, it will demagnetize the permanent magnet. Okay, so if I draw it, if I have a permanent magnet, let's draw it like the old-fashioned way, where I have a big permanent magnet, N and S, and I have a magnetic field, and I put a wire inside. Now this wire creates its own magnetic field, as we discussed many times before, and this magnetic field is like placing another magnet inside this magnet. But if the magnet I put in, which is created by the wire, is much stronger than this magnet, it will reverse magnetize this magnet. Because the way this was made a magnet, it was magnetized by a big coil. But the way it was magnetized, it can demagnetize. So if those of you don't know it, the way you make magnets, you put a big coil around them and send a huge pulse of current. That's how it magnetizes itself. Okay? Well, I'll talk a bit more about it when we talk about moving magnet actuators. But if you put a huge current inside, it's the same as remagnetizing the magnet. So basically there is a second limit, and this is the limit for pulse mode. So for steady state, this is the approximate limit. It's easy to remember, 100 G. Okay? For pulse mode, the limit is demagnetization. And of course here the limit is not a hard number, because you can make this magnet bigger and bigger. So if you want an actuator which works steady state, you can make this magnet quite small, because nothing will demagnetize it. But if you want an actuator which has to work at very fast pulses, at huge acceleration, you can make this magnet huge. So it will be very difficult to demagnetize it. Because this magnet doesn't have to move, so you can make it as big as you want. Okay? And that's why you see on actuators which have to move fast with pulses, sometimes you see a huge magnet. Okay? For example, loudspeakers. Loudspeakers have fairly strong magnet and fairly big magnet because their average current is low, but from time to time you get some pulse in the music. When somebody hits the drums, the loudspeaker has to jump. You need a very big current, so you want to make sure it doesn't demagnetize it. So for moving coil actuators, which have to work beyond that number for a pulse, you have to make sure you don't demagnetize. Basically means big magnet. Okay? So now when we look at this formula, now we can start thinking maybe there is another degree of freedom. Instead of using copper, maybe we should use other materials. So what we're looking is a material which has the best ratio of current density to weight, to density. Because gamma is the current density, so we're looking for the best conductor. Because the reason why you have a current density limit is because of I squared R. I squared R gives us this limit. So maybe we should find a material which has less R, or find a material which has less density. Because the performance is very simple. It's just 3 material constants. So, okay, yes?
Cooling.
Very good point. I didn't talk about cooling. If you force cool it, you can increase this number a lot in steady state, and that's being done. That's being done, for example, in very high performance electric motors, in things where you really need the performance and you can't afford the weight, you force cool it. But this whole calculation is without cooling. If you use force cooling, you hit this next limit. Even in steady state, you'll demagnetize. There's many force-cooled electric motors for high performance. Okay, but the first question is, are we using the best material? Because we're talking about copper all the time. Maybe copper is not the best material. So what conducts better than copper?
Silver.
Gold is not a good. Silver. Gold conducts less than copper, actually. It's just beautiful, but it conducts less. So the only thing which conducts better than copper is silver. It only conducts 10% better than copper. As you know, different copper alloys conduct differently, but there is a standard copper alloy used for making coils. It's called oxygen-free copper, and this copper conducts 90% of silver. So all the coils you see are all made from this copper. It's called oxygen-free copper. So, because strangely enough in metals, just a teeny bit of alloying element kills electrical conductivity and thermal conductivity. Something you probably know, that in all metals, the electrical conductivity and thermal conductivity are linked by a constant. So if a metal conducts heat twice as good as other metal, it also conducts electricity twice as good. Because both thermal conductivity and electrical conductivity come from electron mobility. So in the same constant. The equations have the same constant. But for some reason I found out most students don't know that. That in metal, thermal conductivity and electrical conductivity are the same things, are linked. In non-metals it's not. You can have a ceramic which doesn't conduct heat at all and conduct electricity, or the other way, ceramics or other materials, non-metals, which conduct heat very well and don't conduct electricity. Like beryllia conducts heat like a metal, but doesn't conduct electricity at all. Okay, so we can go to silver, but we only gain 10%. The density of silver is about the same as copper. So we can gain 10% going to silver, but it's a lot of trouble. Has been done though. Okay, at times where you need the utmost performance, you make the coils from silver. The most classic example is cyclotron coils and the coils of the isotope separators in World War II Los Alamos project. Because when they did the A-bombs, they needed the strongest electromagnets possible to separate the isotopes, and I believe also for the cyclotron. So they went to the US Treasury and borrowed all the silver that the US Treasury had, made it into electrical wire, and after the war remelted it and returned it, and the amounts checked out to within an ounce. So they returned all these tons of silver and nothing was missing. Okay? So people have done it in the past, actually made huge coils from silver, but the gain is only 10%. So what about, okay, so if we can't do much better on density, what about this? Can we find a metal which maybe conducts a bit less than copper but weighs a lot less? Aluminum. So that's the answer. So basically, aluminum weighs about a third of copper, right? Because copper is 8.8 roughly. So copper is 8.8 ton per meter cube, aluminum is 2.7 ton per meter cube. So roughly speaking, aluminum is a third of copper, but the thermal conductivity is maybe 60% of copper. Depends on the alloy, depends on many things. So the ratio of current density to physical density for aluminum is much better than copper. Okay? Because this number is a 0.6 roughly, and this number is 0.3 or even 0.5 and 0.3. So roughly it's almost double. Again, depending on the alloy and so on. It takes more space, because in order to carry the same current, you have to make the wires bigger. And if you make the wires bigger, you have to make the air gap bigger. So you lose a little bit on B. Right? If you have the same coil with the same number of turns made of aluminum, to carry the same current, the wires have to be a bit bigger, because otherwise R will be bigger. You want to keep I squared R constant, same heat. So if I is constant and the resistance is higher, you know, you have to make the A bigger to keep the resistance the same. Is that clear? That's why in the old days when they wired some houses in BC with aluminum, the gauge was higher. Like instead of gauge 16, you put gauge 14. Okay? But overall you gain. So maybe I went too fast. Is that clear what I said? If the wire is aluminum doesn't conduct as well as copper, so it gets hot. Okay, so in order to keep the heat down, the aluminum wire has to be a bit bigger. Okay, so that means the coil is a bit bigger, and the problem it causes, if you want to fit the coil inside the magnet, and you make the coil of aluminum, it's a bit bigger, you have to make the gap a bit bigger. And if you make the gap a bit bigger, B goes down a little bit. I wouldn't take you through the whole optimization, but you can envision it, right? Because if B goes down a little bit, it cancels some of the gain. Because the ratio of current density to physical density, let's say, is 1.6 or 2, but you have to discount another 10% because B will drop a little bit, because you have to increase the gap. Anyway, you can go through this whole calculation. I wouldn't bother you with it. So the bottom line, it's still like at least 30% better. And because of that, the highest performance actuators are actually made of aluminum wire. Can somebody think of an example? Where do you see aluminum wire used today? In actuators. High-end speakers. If you buy the highest end speakers, the coils inside are aluminum. Because in a speaker, you know, this extra 30% means something to high frequency and so on. Okay? But really you can't gain. Silver gains you almost nothing and costs a lot more. Aluminum gains you a little bit, but because B drops a bit, the overall gain is maybe 30%. So most of the cases it's not worth it, because as you suggested, you can use cooling. Because other alternative, use copper, put a big fan, and the fan cools it, then it's actually a simpler solution. And that's what they do. They basically use forced air cooling or liquid cooling. Okay? So, bottom line is that if you have to design a servo, and the servo has an actuator which has to do much better than 100 G, you're looking for trouble in a steady state. If it has to do more than 100 G in pulse, it's no problem. Pulse mode, you can go easily 10 times that number. So if it was a pulse, you can easily go 1,000 G up to 10,000 G before you hit some other limits. Here you start hitting demagnetizing limits and other limits. Okay, and the last thing I wanted to point out, and this is something which I find out that most students don't understand, that if you have a current like that, if you have a current like this, let's say you have 10 amp, and this is 10% of the time. So you have 1 second. During this 1 second, for a tenth of a second, you have 10 amp. And I want to calculate to what DC current this is equivalent. Because the heating is derived by an equivalent DC current. So if I want to convert this 10 amp for 10% of the time to DC current, what would be the DC current which will replace it in terms of heating? So a lot of people say 1 amp. Because this average of this is 1 amp. But what is the correct answer? Okay, the correct answer, yes?
Square root of 10?
Yes, the correct answer is 3 amp because the heating is proportional to I squared R, not to IR. So you can't take the average, you have to take the RMS value, right? And the RMS, does everybody know here what RMS value is? Yeah, I sure learned it enough times. Okay, so you have to take the RMS, so you have to take basically 10 squared, okay, square root of 10 squared times 0.1 and divide by 1, okay, and then you end up with 3 amps roughly. So the equivalent heating of that pulse is like a 3 amp, and the narrower the pulse, the bigger the ratio between RMS and average. So the more dangerous it is if you pick the average instead of RMS. Okay, so say if this was 100 amp, if this was 100 amp for 1% of the time, the average is still going to be 1 amp, but the RMS will be 10 amp. Is that clear? So that's very important when you design actuators. Okay, any questions about this? Good. Okay, thank you.